Okay, so the case of two connected conducting spheres with a certain charge can be a little bit of a tricky problem, so I'm going to go over that today. So we have one sphere with some radius r connected by a wire to another sphere of some difference radius, big R. And between the two of them, they have some total charge, big Q. And the question might ask you to find how much charge is on each sphere, or what is the voltage, or something similar. Either way, the process is pretty much the same. So first of all, we have to figure out what actually tells us what is the relationship between the amount of charge on each of these spheres. Well, since they're connected by a conductor, as far as we're concerned, we can kind of treat them as one big conductor. And for any single conductor, the surface of that conductor must be an equal potential surface. And to kind of understand why that is, I want you to think about what a potential difference really means. A potential difference will result in an electric field, a non-zero electric field, which will exert a force on any charge. And of course, within a conductor, charges are free to move. So if there's any potential difference within this conductor, charges are going to start moving around, and basically the charges are not going to settle where they are. So the charges are going to freely move around according to the potential differences until they find a state where there is no potential difference. So whenever we solve a problem like this, where we're looking at an unchanging state, we need to find, or we know that the potential difference anywhere in the conductor must be zero. So we can set up an equation just using the formula for the potential of a sphere near the surface of a sphere of charge, which is negative kq over r. So we'll find for the first sphere, this is actually exactly as I wrote it, negative kq1 over r. And for the second sphere, this will be negative kq2 over big R. And these must be equal because, as we just discussed, voltage must be equal within one continuous conductor. So now the other equation we can write out is that the sum of these two charges must be equal to our total charge. And between the two of them, these two equations, we now have a system of equations that we can actually solve. So we can write Q1 over R is equal to Q minus Q1 over big R, just substituting in that equation into here. And we find RQ1 is equal to QR minus Q1R. And now if we simplify a bit, we find Q1 is equal to QR over big R plus little r. And now, so we found the charge on the first sphere, the littler sphere, the sphere with radius little r. And now if we just use this equation up here again, we can quite easily find the other charge as well. Q2 is equal to big Q minus Q1, which is going to be equal to Q minus QR over R plus R, which works out to Q big R over R plus R. So there's two of the quantities you might be asked to find. The last one that I can think of right now would be the voltage at the surface of this conductor, which we simply use one of these equations for. So negative kq over r. So the voltage, we can just use either q, is negative k q r over, let's see, we're using the big R here, so we're going to have to use the big R again for the denominator, R plus R. So that might have been a little bit confusing, but you can see this chunk right here is just the Q2, and that's replacing the Q1 in this equation. And then we just have negative K over R, and this R must be, of course, the same radius corresponding to whichever sphere we use the charge for. And since we used Q2, which was the big R sphere, we have to use the big R in the denominator. So then we can simplify this a little bit to find that the voltage is equal to negative kq over r plus little r. There we go. So now you know how to find the voltage and either charge in a system of two connected conducting spheres.